SwayamPrabha. Digital India. Educated India.
So, let us start the slurry reactors, okay. And this is the last part. We have done fluidized bed, packed bed, and now this is slurry reactor, 3-phase reactor, right. So, the objective in the beginning, of course, even though first day I did not mention, generally I was telling that we should understand for heterogeneous systems how do you develop that rate equation, right. And we have taken some examples including slurry reactor at that time, okay. Catalytic reactions, non catalytic reactions, but mainly the course has been divided into 3 parts. Okay. The first one is of course introduction and all that, then we have non catalytic part which we have done, and we used the same fundas what we have discussed in the first part. Okay. That means identifying the number of steps and writing for each step the equations, eliminating the intermediate steps. In all these things, that is the common thing. So, when I was given that award, they asked me to speak, I told the same thing. I have a beautiful quotation by some J.P. Epstein. I think he told that I am not telling great teachers, I am not referring to me. So, the quotation is that great teachers just not only teach the subject matter, but they teach an attitude towards the subject, okay, an approach to the subject. Without knowing myself, that is what I have been doing it. Okay. So, now you have an approach to the subject. I do not know whether you understood or not, but you have an approach to the subject. What is the approach? All heterogeneous systems, there is only one approach. Identify the system first, whether 3-phase, 2-phase, catalytic, non catalytic. Then you can imagine the entire system in terms of steps. What is step 1, what is step 2, what is step 3. So, once you have this idea in your mind, try to put on the paper how to draw the profiles. Even yesterday also we have done that. So, the moment you have drawn that profiles, then mathematics are very simple, because in the first profile what is the equation, second profile what is the equation, third profile what is the equation, then what do you get? An average and a global rate. Once you have the global rate, you already learnt contacting. Fortunately, you have only 2 contacting continuous, 1 batch, right. So, you with this information of global rate, you have to just go to the correct contacting pattern, substitute and then integrate. Even yesterday we have integrated, and we have taken the contacting pattern for gases, plug flow and other steps, and you got indirectly what is called an effective rate or a global rate, observed rate. That is what we have I did even yesterday for fluidized beds. So, fluidized beds very thoroughly used, I think most of the time used in the industry, that we have done thoroughly. Packed beds we have done thoroughly, but before doing packed beds we spent some time on understanding the catalyst. Okay. So, that means what is the how do you design the size of the catalyst, for example, without having diffusional limitations, and what is effectiveness factor, what could be the temperature profiles, concentration profiles, all that may be required for actually understanding the packed bed catalytic reactors. Not only packed bed, even slurry reactors, even fluidized bed reactors, because individual particles are there in all these. So, you should know in the individual particles whether there are any concentration gradients or temperature gradients. Our preference is you should not have temperature gradients, or also you should not have any concentration gradients. Then you will get the maximum conversion or rate for the particles. The moment you have maximum rate, you will have the minimum reactor volume. So, that is what is the objective. So, that is all. That is an approach. That is really an approach. Okay. So, that is what we are trying to do, and the last part is slurry reactors, where we have now here 3 phases. Okay. So, please take this one, a slurry reactor with 3 phases in the bracket gas, liquid, solid, we do not have any other, no, may assume various forms like stirred tank, bubble columns, stirred tanks, bubble column, sieve tray, staged reactor, but whatever the geometry, the reaction phases are gas in the bracket reactant, comma, liquid in the bracket reactant / inert, it can also be inert liquid, bracket closed there, that is liquid, and solid in the bracket catalyst. Yeah, the catalyst, the solid catalyst is suspended in the liquid in the presence of gas. in the presence of dispersed gas. Good. Okay. Next para you can write examples are one, hydrogenation of vegetable oils, hydrogenation of vegetable oils. Okay. So, here what is gas, what is liquid, what is solid. So, this is unsaturated oils. Sorry, yeah, okay, okay. This is hydrogen, this is oil unsaturated, this one is catalyst nickel, nickel catalyst Ni. Okay. So, the another one is polymerization of ethylene or propylene. Here we have again gas, liquid, solid. Yeah, gas is of course ethylene or propylene correspondingly. Then we have solid catalyst. I do not have I mean what is the correct catalyst is sorry, yeah, solid Ziegler, Natta, right? Yeah, right. Yeah, and liquid is cyclohexane. How do you know? You worked in polymer industry or what? This is cyclohexane. Okay. So, that is another example, and here the presence of cyclohexane is not to participate in the reaction, it is only to absorb heat. It is a very good heat absorber, because lot of liquid will be there. So, that can take a lot of heat. So, the third one is, have you heard of this Fischer-Tropsch synthesis? TROPSCH, Fischer-Tropsch synthesis, where you have here gas, liquid, again solid. Yeah, gas is no hydrogen or CO, hydrogen and CO, not CO. Okay, that is the one. Then we have solid iron catalyst, and liquid is hydrocarbon oil. Okay. So, I mean just want to justify that we are not discussing something totally academic. Okay. So, slurry reactors are very widely used in industry for many purposes. That is what is the beauty in chemical engineering, I have told you. So, how many chemicals you can list? You can list thousands of chemicals, right. So, each chemical has a beautiful history, beautiful process, beautiful family of reactions, all that. So, that is why really we are very lucky, because you can never get satisfied with all these, and each chemical may have 10 different processes, it is not one, maybe directly, maybe after 2 steps, maybe after 10 steps, all that we have to decide which is economical, that is all. That is why it is totally open field. I think this kind of opportunities in no other engineering you have, because they do not have chemicals simply, right. And chemistry, I say, that is why we are the where chemistry stops, chemical engineering starts. Okay. This they have been telling, when I told last time also in chemistry department, they were very happy. So, who are the starting points for you, but I think yeah, they were the starting points for us, that is true. They only make, they are making so many chemicals, and they stop only with 1 gram, 2 grams, 1 microgram, or maybe 10 grams maximum, that is very big scale, 10 grams. But for us 10 grams I think is not even a scale. Okay. So, that is the problem. So, it can go to tons, ammonia if you take 10,000 tons per day, 10,000 tons per day, you can just imagine in one plant. So, I think all engineering problems come the moment you go for larger and larger productions. Heat transfer is a problem, fluid flow is a problem, okay. Like everything, filtration is a problem, crystallization is a problem on large scale, and heat maintenance is a problem on large scale again, because I told you, I think a chemist will take most of the time the reactor is test tube. So, you will go to the Bunsen burner, put there like this, reaction complete. So, then he goes to the gas what is that chromatograph or some HPLC, and then tries to find out what is the conversion. But can you take our ammonia reactor, which is I think 2 meter diameter and height may be some 15 meters, 40-45 feet, then take it and then shake? Impossible. So, then that is the reason why you should now have what kind of heat transfer you should have. What is the mode of heat transfer? How do you remove the heat, or how do you add heat? So, that is why I said that statement is very good, where chemistry stops, chemical engineering starts. Okay? But it is not their business to go beyond that. Okay? Even though sometimes we go to their business to find out whether this reaction is, can I also try. That is why we have lab scale, we have bench scale, we have pilot plant scale, then we have industrial scale. Why? Why so many scales, by the way? Not cost. Particularly fluidized bed is a deadly example for this kind of scale up, because on a small scale fluidized bed, when I construct in the lab, the type of bubbles I get, okay, and the contact between solid I get, the moment I go for large scale, totally it may be different. So, that is why in between I would like to see what is how this phenomena is changing when you go to very small, slightly bigger industrial scale. You see, you would have seen books also, scale up in chemical engineering, there are books, scale up rules are there. Okay? That is the problem, because particularly when you have 2 or 3 phases, then all these problems will come. Particularly when you have bubbles and drops and particles, the scale up problem is automatic. And in which process you do not have bubbles, drops and particles? In every process we have. So, that is why you cannot escape. That is why Kavya, beautiful subject is chemical engineering. No, you do not agree? Still you are sleeping? No, okay, good. Yeah. So, that is why I thought I will just give you some ideas about this. Okay, good. So, advantages you can just write. Advantages: 1, the high heat capacity of the slurry is conducive to isothermality. Yeah, and number 2 is heat exchange, and therefore, heat recovery is very good. See, sometimes you can put even tubes inside the slurry reactor, if it is very highly exothermic reaction. Okay. The liquid is not entirely take up this heat, because the temperature of that may be increasing beyond certain value. So, then you can also put inside tubes and all that, because it is liquid. So, easily heat transfer will be more. So, that is what is the meaning. Number 3 is very small particles can be of course, we need smart particles. Very small particles can be accommodated without intraparticle diffusion. Correct? No, smaller the particle, the diffusion length will reduce. So, without intraparticle diffusion. Number 4 is the reactor can be simple stir tank or autoclave. Stir tanks we are famous, no? So, easy for design. So, that is the simplicity. The reactor can be simple, for example, stir tank or stirred autoclave if you are using pressure. What could be the disadvantage? Because for everything there will be something bad. Relative velocity between the particle and then liquid is one thing, relative velocity, because mass transfer may not be high. The other one is product separation, particularly. How do you separate the particles from the product? You have the catalyst particle. So, that is why sometimes when you use dalda, be careful in the hostel, sometimes you will get nickel particles, that is the product separation, iron nickel particles, sometimes you may get, right. So, that is why you have to be careful, particularly in the product separation, right, because those are solids, gas anyway will go, no problem, and liquid and solids you have to separate them. So, that is one of the problems there. Okay, good. So, now what is our approach? Our approach is to have the reactor first. So, the reactor may be like this is a simple vessel, then we introduce gas, this is simple pipe, of course, you may have sparges and all that, this is gas. Yeah, so here you have the liquid and you have the bubbles, in fact so many bubbles. Yeah, so in between you also have solid particles. Yeah, so we have this is liquid. Okay, so here I have liquid, gas may be coming out here. So then this is bubble, that is gas phase. Then we have here one particle, I will show you slightly bigger. This is catalyst, solid. So this is the picture. So then if I also take one bubble for our imagination, okay, right, and also you have inside gas film. If I have different gases, this is gas film, this is liquid film, because all surrounding I have liquid, right. Yeah. So then somewhere here I have catalyst particle, right. So then again this has a liquid film, right, this also in the liquid. So now we know the steps. The reactant gas in the bubble should first come through the gas film, and this is the interface, gas liquid interface, and this is liquid solid interface. Okay, you have two interfaces. So the first step is the gas should come through the gas film, the reactant gas, then it has to cross this interface and then go to the liquid film, right. Then it has to cross the liquid film, then it will dissolve in the bulk liquid. So after dissolving in the bulk liquid, then it can go to the liquid film again, which is surrounding the solid particles, catalyst particle, and then it has to touch the surface. If the particle is not porous, then reaction occurs only on the surface, or if it is porous, then the reaction again the reactant has to diffuse inside, but now it is in the form of not gas but liquid, correct. No, the gas has to dissolve in the liquid, that liquid dissolved reactant will go to the internal pores and then it will get reacted. And we are experts now how to take care of, even if I have this porous particle, then if I know the effectiveness factor of the particle, then I will know the rate of reaction in the particle. Okay. But that reaction definitely depends on what is the concentration here, 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 what is the concentration there. Good. So now this phenomena we have to now just show in the form of profiles. Okay. So that profiles, let me draw. We have okay, let me write concentration profiles. So we have, this is the gas film, then I have here liquid film, this is gas film, liquid film. What is this one? This is in fact GL interface, GL interface, that line. Okay. So here I have bulk gas Cg, I am not using any A there, that is the bulk that means I have here the bubble, right, a bulk gas, and anyway afterwards we will draw the other one also. Then we have here the bulk liquid, and okay, I will also draw highly exaggerated, but still okay. This is the solid. This is solid. So, this is again liquid film. Good, that is the liquid film. Then this is bulk liquid. If I remember correctly, I have given this one as a surprise test. I think most of you also written this. Okay. So, then we have here a concentration drop. This is CGI, right, and depending on your Henry's law constant, this can be CL of I, and CGI, CLI are related with Henry's law constant. Okay. Then from here again it goes to bulk, and this is CL. CLI is interface, and from here what we normally assume is that we have constant CL. Okay. That means because of vigorous mixing, this mixing can be here because of large agitation created by the bubbles, or it can also be if it is not sufficient, because particularly when you have heavy catalysts, high dense catalysts. So, they will try to settle, because the buoyancy created by gas bubbles may not be sufficient. So, that is why you also put sometimes external stirrer, impellers. Okay. And that impeller will also serve as the gas distributor as well as mixer. It can also create very fine bubbles of gas. Okay. That also possible. So, then from here it goes to CS. Okay. Cl to CS. Good. So, now what are the steps here? Of course, steps I will write. Step 1, empty of gas, mass transfer of gas through gas film. Step 1, sorry, step 2. Then we have empty of gas through liquid film, of course surrounding the bubble. So, step 3, that is bulk, dissolving in bulk gas. Step 4 is that dissolved gas has to go to mass transfer of dissolved gas now. Dissolved gas through liquid film, through liquid film. And step 5, reaction on the surface. Okay. Reaction on the surface. Okay. So, we can also say if I have a porous particle, then it is now diffusion through the particle, right. Next step will be diffusion through the particle, then reaction. But anyway, that step can be combined as a step with Fitness vector. Okay. Good. So, now when I write the equations for this, which you already know, the overall rate, observed rate must be equal to kg mass transfer coefficient through this. We introduce it here, as Ag Cg minus Cgi, where Ag I will tell you, Ag is you have surface area, bubble liquid interfacial area, Ag please write. No, I think we can write that later after writing all. So, this is also equal to, under steady state conditions, that is also equal to KL Ag Cgi minus Cl, correct? Okay. Which of course you can write through the other equation. Then I also have Kc Ac Cl minus Cs. Huh? Yeah, you can later. Later you can substitute. I will give you the another equation. Okay. Yeah. So with the Henry's law you can substitute that one as Cli. Okay. Yeah, I think correct. What she said is correct, because you are talking about this point to this profile, not this discontinuous profile. Right, you are right. Yeah. Okay. So now of course you can add this one here Cgi as H in terms of H, then you can cancel out all that. So that is correct, Kavya. Thank you. So then we have the next step is all these 3 steps, mass transfer steps. Then we have rate of reaction step, where we have eta k Ac Cs. So if I take this one as 1, 2, 3, 4, right. Then you have the fifth equation, that is Cgi equal to H Cli. That is the equation. Good, very good. So this you have already done. That means eliminating all the using this, eliminating all the intermediate concentrations like Cs, Cl, Cl. In terms of Cg, you can write this equation, right. So when you do that, what you get is you have I am skipping because you have already done this. So ROB equal to AC Cg whole thing divided by I have AC by Ag into 1 by kg, that is the first resistance, AC by Ag H by KL plus H by Kc Ac plus again H by eta K Ac. So this is the rate equation. Okay. So this is equation number 6. Now I have to tell you what is AC. You can please take that. I think all other things we know, all mass transfer coefficients. H is Henry's law constant. AC is bubble liquid interfacial area per unit volume of Ag. First Ag equal to bubble dash liquid interfacial area per unit volume of, it is expressed as per unit volume of bubble free liquid, okay, or in the bracket slurry, bubble free liquid. That is bubble liquid interfacial area per unit volume of bubble free liquid or bubble free slurry. AC is next one. AC is external surface area of catalyst particles per unit volume of bubble free slurry. Okay. And ROB, this also please write, ROB is expressed in moles per meter cubed bubble free slurry per second. Minus RA is expressed as moles, because I know that I have to clearly define, every time when you talk about heterogeneous systems. Okay, we have to define, otherwise you will have problem. So RA is expressed in moles per meter cubed bubble slurry, okay, bubble free slurry per second. That is the rate of reaction. Good. So now as usual, like in the yesterday's thing also, this is the rate expression now, overall rate. Now I have to find out corresponding contacting pattern. For example, if I want to use that equation for bubbles here, gas phase, right. So, gas phase will be moving in the form of, simplest assumption is moving in the plug flow. So, now I have to use V by F A naught equal to integral 0 to x a dx a by minus R O B, where this is the minus R O B. Okay. So, now when I want to integrate, for example, it is a first order reaction, this C g will be written in terms of conversion. If it is no volume change, C g equal to or any time C g equal to C g naught into 1 minus x a or x. Okay. That you have to substitute and then integrate, you will get first order very simple ln 1 minus x, but all this. So, when I want to use this, the next step is to find out, how do you find out AC, AG, KG, KL, KC, K. K is the intrinsic rate constant. So, this is an approach I have been telling you. Now, you take any system, I do not have to do now gas liquid, because gas liquid is already part of it. If I am stopping only here, then that will be equal to gas liquid bubble columns, right. So, then liquid, but only thing is replace this gas with liquid, extraction, okay, extraction with chemical reaction. So, then I have two phases, I mean two different liquids, then I have one liquid film, another liquid film, then the procedure is same, approach is same. So, that is why entire heterogeneous engineering, even though we have not done the details are how to find out, for example, mass transfer coefficients. The beauty in heterogeneous system is there will be 6 or 7 mass transfer steps and only one will be reaction step. Okay. So, all the time it is now for us, our duty is to find out mass transfer coefficients, and if there is a problem with heat transfer, also heat transfer coefficients. Here we do not have to worry about heat transfer, because isothermality is maintained throughout the inside the particle, okay, because small particles, and also inside the liquid, because I have large amount of liquid where all the heat is absorbed and liquid is moving very vigorously. So, uniformly the heat is distributed in the liquids, you will get isothermal temperature. Okay, good. So, now quickly we will try to find out how do you, there is another thing here, even though there are some correlations for Kg, okay, most of the time this will be the, it is not at all rate controlling stuff, that will be the much faster, because gas diffusion is easiest one. In the bubble I have here, let us say two gases, hydrogen plus some other gas. Hydrogen can happily go without any problem, whatever gas you put there, because that is the lightest. Okay. Diffusion is very easy for that. That is why very fat people cannot move faster, and a very thin person can go like this, like our autos on the road, okay, or motorbikes on the road, like this you will go, right. That is diffusion through the packed bed, particularly if you go around 9 o'clock to 9 o'clock to Mount Road, then it is a packed bed, and you can see the hydrogen molecules moving through, that is autos slightly bigger molecule, and two wheelers hydrogen, less than hydrogen, less than two wheelers, what equipment we have? Cycles, but cycles police will not allow them, otherwise cycles also will go through. So, that is what is the diffusion there, that is all. So, that is why that is easy. So, most of the time this diffusion, gas diffusion is easiest. So, Kg will be usually very large. So, this will not be present in most of the slurry reactor design expressions. Okay. Kg can be safely ignored, in the sense that it is not ignored, Kg is so large. So, 1 by Kg, that term will be 0. So, you can remove that. Then you will have only the remaining 3 terms, okay, KL, particularly 2 terms, because this is the intrinsic rate constant, and it depends on your ingenuity how to find out this K without any interface and intraphase transport processes, like we have discussed. That is one of the very difficult problems, but we have not done that, and so that is why most of the time we will try to express this in terms of eta phi square, which is observable. Here also you can do that, right. So, that was the reason why eta phi square observable we have gone, observable equal to ROB L square divided by dE CB, CG or CB, okay, bulk. So, that is what is observable, because CB dE you are supposed to know dE, okay, through correlations and all that. So, then the shape of the particle we know L square, and also rate you are measuring, okay. Using that K also can be calculated. In fact, K can be estimated using this technique, that is pure intraphase intrinsic constant, where you measure all this, then you can separate from before converting that into eta phi square. What you have done? You have actually eliminated k from that, if you remember the original derivation. So, you can go back finally there and then substitute and get pure k, that can be done. So, now the rest is k L and k C, and k L mass transfer coefficient. You see now automatically, actually these last few classes are very important classes. Till now what you have learnt is only the background, okay? But unfortunately climax comes only for some time, okay? Climax cannot be 40 classes, okay? Climax will be last for 3-4 classes, where all the knowledge will automatically come here, okay? Correct, no Beulah? Yeah, good. So, she is a teacher, so that is why I asked her. Okay. So, that is why for any system this is the now procedure. What is that? Write the equation, find what are the things not known, and I can tell you people have spent their life only to find out KL. That is all, the entire life. There are so many correlations. If you go find out in slurry literature what are the correlations for KL, there will be at least 50-60. That means 50-60 people minimum should have worked. Because each one will have his own correlation, not one, normally professor and his student. Okay? And if you go to some other departments, each paper, even though it is PhD work, 5 students' names are there. This has become a fashion now in some science departments. Okay? Then I do not allow that. I mean, I am asking as a dean that in synopsis meeting you cannot have in PhD 5 names. Naturally, examiner will have a doubt there who has worked out of 5. Correct, no? 5 names means, I mean, you are all equally supposed to contribute to that paper, that is why 5 names are there. So, that is why I request the HOD and also the individual faculty members, please do not put this kind of practice. At least there must be 1 or 2 papers for that particular student on his or her name alone, because that she can proudly say that this is my work. Otherwise, she is 1/5 of the crowd. Okay? Yeah, beyond 3 we call crowd, no. So, that is why I think 5, 6 are common. So, that is why I told you, that is why at least minimum, if it is single other papers, you should have 50 people would have worked there, and 50 people would have worked lifelong, that also on that. So, like that same thing with Kc and effectiveness factors here. Okay? So, that is why what we are telling here is some of the correlations, they are not the only correlations that are available in the world, okay? But some correlations which have come to the textbook means it is accepted by many other people. So, this information I am taking from Smith, chemical engineering kinetics, okay? This information. Okay. So, now mass transfer coefficient MTC KL, this is bubble to liquid, okay? Bubble to liquid. Yeah, even in fact this equation also will change the moment I see that yeah, here. So, this is now horizontal almost, there is no concentration gradient there. So, we will have there CGI and CLI related directly. Okay. So, now I can express this equation in terms of CLI. That is another very simple thing, because the reason there is, it is very good for me to estimate concentration of gas dissolved in the liquid is much easier than estimating the gas concentration, because gas means again HPCl, something like that, or gas chroma GC and all that one has to use. Okay. So, that is the reason, that is also another simple thing there that will come. Okay, good. Of course, HCl, H also will come. So, simply this will become HCl equilibrium, because Henry's law is in equilibrium law. No? Yeah, good. So, this is KL is bubble to liquid, that is the mass transfer, because always when you say mass transfer coefficient, your question should be immediately from where to where, okay? Otherwise you do not know where to where. Good. So, you have KL equation given as 0.592, this is diffusivity, gas diffusivity to the power of half sigma by nu to the power of 4. If I go to 6, this is 7. Okay. So, now where sigma is n p rho l n cubed d I to the power of 5 by w into 5. So, this is equation 8. I think here we have to write where no, okay, again where d okay, I think all we have to write. Okay. First let me write d I is impeller diameter. Now, you can see that means they have used an external impeller in the reactor. Okay. Impeller diameter, this is in centimeters, and d this is molecular diffusivity, of reactant in liquid. So, this is centimeter square per second, that is diffusivity. Then I have nu kinematic viscosity, then I have K L, K L is of course, this is MTC liquid side, units simply centimeters per second. Then we have n, small n, RPS, okay, revolutions per second. Then W, mass of slurry, mass of liquid slurry, slurry means liquid only. Yeah, this is grams. Yeah, anything else is missing? Rho L of course is centimeter square per second. Yeah, what did I write? Okay, units I have not written. Yeah, write it, centimeter square per second. Okay, good. Yeah, so then the next rho L is the density, and now N P, yeah, N P has another equation. I think I have to remove this. See, everything that has a beginning has an end. So, even it is so beautiful I have written, it has to go sometime, correct? No, only God does not have starting point, does not have end point, that is all. Okay, good. So, N P, see the problem, that is why I said lifelong these people would have worked only on this. Now, N P has another equation, power number where this is equal to capital P rho L liquid density n cubed. So, this is equation number 9, where phi is a correction factor, given by phi equal to 1 minus 12.6 q by n d I cubed. This is equation thing where q equal to q, q this side, phi this side, q equal to gas flow in centimeter cubed per second. Okay. You see now, just to calculate KL alone, how much work would have gone, particularly when you are using impellers. Okay. So, KL equation is that is related to sigma, sigma is there in that equation 7. Now, to calculate sigma you also need phi. So, phi and NP. Yeah. So, NP has another equation, phi has another equation. So, that is why you really scold me if I give this in the examination. Okay. Correct, no, Prabhu? Yeah. Why? Because you do not want to learn. You really appreciate me. You really appreciate me if I give this in the examination, because wonderful problem, because it is a real problem. Okay. Good. So, this is one correlation. There is another very simple correlation where you like it. Yeah. P is power. Yeah. Not yet come. Yeah. Ergs per second. Oh, that has not come. Right. 2. So, P equal to power ergs per second. Anything else missing? Yeah. So, that is why we have another equation for examinations. Okay. So, another equation for examination is that do not use agitator, then you do not have to worry about power number, RPM, RPS and all that. So, without agitation, in the absence of, that is mechanical agitation. Okay. So, without or in the absence of mechanical agitation, in the absence of mechanical agitation, you have K L equal to mu L liquid all, rho L, and of course, d diffusivity. So, this whole to the power of 2 by 3 equal to 0.31 delta rho, that means rho L minus rho g, into mu L g by rho L square. So, this is the equation 11. Okay. This KL can be used to find out the mass transfer if you do not have mechanical agitation, if you simply bubbles are going with buoyancy, right. Good. Where all the other things we know, no, rho L we know, mu L we know, mu L is the viscosity of the liquid, that delta rho is the density difference, g we know, the d is the diffusivity, all that, fine, excellent, good. So, that is the one for KL. So, now you have KC. KC we are saved because we do not have that we can fit in the form of equation, but we have a graph, Sherwood number versus what should be the other number for Kc. So, this is in fact 1 and number 2 is MTC Kc liquid to particle solid. Okay. Yeah, actually this is the real life, right. Actually real life, to give an example, all romance will be only for 1 year before marriage or after marriage. Okay. Afterwards reality, this is reality. And you know what has romance? Beautifully writing this step equal to this step, this step equal to this step, this step equal to this step. Okay. And finally, you have that equation, that is the reality. So, now that equation contains unfortunately this KL, KC, K eta and all that. So, you have to go for only correlations where there is no romance in correlations, correct, no? Where is the romance in correlations? Because I think someone has to really work very hard, and after working maybe 5 years, 6 years for PhD. So, finally, you will give one equation. Okay. So, that is why all chemical engineering design people will not like, because there is no romance, simply absence of romance. Whereas, I think the other steps are, for example, drawing this and then writing the steps, eliminating intermediate concentrations. Okay. So, then even if you do not like and then if you hate that one as romance, you are not good for anything. So, that is why you have to either like this or like that or like both. Okay. So, you do not have a choice now. So, for Kc we should have another correlation. So, that correlation this again agitating speed and all that, please take this introduction I think we will have. Yeah. Okay. The relative velocity between particle and liquid determines the extent to which convection increases the Sherwood number above that for stagnant conditions, comma, that is above, you tell me the value, above dash. I know you have not understood what I said there. You have simply written there without understanding. The relative velocity between the particles and the liquid determines the extent to which convection increases the Sherwood number. Above that for stagnant conditions, that means for stagnant conditions what is Sherwood number? Excellent, above 2. The 2 is the minimum basic, right. So, when you have I told you, no example, come with beautiful scent and then sit here. Now, this is still, there is no movement of any gas. So, the smell comes by diffusion. Okay. So, then if someone puts the fan behind, then that comes convection. So, now the total mass transfer is that fan speed, convection plus diffusion. Okay. The diffusion is 2, Sherwood number equal to 2. That is a beautiful derivation. I do not know whether anyone of you have done it in mass transfer, and also heat transfer also that comes so beautifully. Okay. So, that is the one, and the basis for correlating Kc as a function of agitation speed and particle size is based on, you heard of this fellow's name, Kolmogorov, transport phenomena or fluid mechanics people would have told turbulence. Kolmogorov's theory of isotropic turbulence. It would have come in other subjects also. Kolmogorov's theory of isotropic turbulence, that is the basis. According to this theory, the Reynolds number is defined, according to this theory, the Reynolds number is defined as Re equal to dP to the power of 4 by nu cubed whole to the power of half for xi greater than dP. Okay. Sigma, sigma is again same thing what we have used there. Okay. Sigma is in ergs per second per gram, that is same as in equation 8, and xi eddy size. Xi is eddy size of the eddy, and this is valid of course, xi greater than dP. Okay. So, otherwise that means if you have xi less than dP, Reynolds number equal to sigma dP to the power of 4 this is 1 by 3 instead of 1 by 2, where eddy size also one can find out, that is xi equal to nu cubed by sigma whole to the power of 1 by 4. So, if I write equations, this will be 12, 13, 14. Okay. Good. So, I think this I have to remove now. Yeah. So, here you have a graph relating the Sherwood number and Reynolds number. Reynolds number defined in that fashion. This is Reynolds number, that is equation 12 and 13 depending on xi values. Okay. So, then here I have Sherwood number. Okay. Actually, this is Sherwood number by, what is this number? Mu L by rho L d, Schmidt number. So, this is to the power of 3, 1 by 3. To the power of 1 by 3, Sherwood number by that is plotted. So, here this is a log scale, I have here 0.1 starting somewhere here 1 and 10. This side we have again 0.1, 1, 10, 100. See, this is another way of defining Reynolds number. So, you have approximately this is 0.2, 0.4, 0.6, 0.8, of course, log scale only. Yeah, then again here I have 2, 4, 6 and 10. Yeah, you will have a line somewhere near 4 it starts, like this it goes. That is the correlation, not exactly straight line, but slightly this way, that way it goes there. Yeah. So, this is the correlation. That means, if you want to design, then I have to give you this, even if you want to calculate, if I give the problem, I have to supply this information and then first calculate Reynolds number. If it is 10, go there, read, and this coordinate you know. So, that is Sherwood number is again defined as K C here. Okay. Yeah. So, that value you have to substitute K C d p by d, diffusivity again. Okay. So, using that you can calculate what is K C from this. Good. Yeah. So, that is the correlation and good. What else is now? Everything we will know. Of course, intrinsic rate equation only other one left, but I think that you have to use some other technique to find out, that we do not have. Then you know some kind of simplifications, right. That equation where you have 3 resistances, so you have to go for the Tiffin or what? Huh? Okay. So, some simplifications for that equation where you have ROB equal to, okay, tell me that equation. I have AC H Cl equilibrium, I substituted there, okay, already. That is correct, no? Anything else missing there? Huh? Yeah. So, this whole thing divided by 1 by kg I am dropping out. So, then we will have AC by Ag H by KL plus H by Kc, AC Kc plus we have H by, again AC will come, no? Yeah, AC eta K. So, that is the equation, and most of the time this equation, if I say 15, I have not written this equation earlier. Okay. Yeah. So, this equation most of the time this term also is neglected. Do you know why? The last one. Neglected in the sense the K must be large value. Why? Yeah, most of the time this ran in nickel and all that, and that too very fine powder what you use. So, very active catalysts only are used for slurry reactor most of the time. So, that is the reason why 1 by K value or K value will be very large. So, this term also will disappear. So, finally, what you have all the time in the design will be H also will get cancelled, AC Cl equilibrium divided by AC by Ag 1 by KL plus H will go AC KL. That is the equation. This is the most practical equation, most of the time people can use that. Okay. So, now again further simplifications, because as an engineer you should be able to simplify things as easy as possible, so that your design will be the simplest, right. So, you also have something in your mind, something that means if I am taking very fine particles, large number of very fine particles, then the ratio AC by Ag will be very large, AC by Ag. Okay. So, then can I neglect this also? AC is what by the by? external surface area of catalyst per unit volume of bubble free slurry. Okay. Do you know how do you find that?
No gas is mass volume.
I mean, if I want you to have develop an equation for that, AC surface area of external surface area per unit volume of the particle multiplied by volume of the particle and divided by volume of the slurry. Okay. Anyway, I think you would have not got that, but I will tell you, because that is also how you find out AC. Then we can discuss that. AC is surface area per unit volume of bubble free slurry. Okay. So, surface area per unit volume of slurry liquid. Okay. Liquid I am writing. Okay. Good. So, now this can be also written surface area per volume of particles, total surface area per total volume of particles, into volume of particle divided by same thing, volume of liquid. What is this surface area per unit volume of particle? I can multiply by n and multiply by n there, number of particles, total volume and surface area. What do you get there? Pi by or 6 by dP. Good. So, this is 6 by dP and this one for volume of particles, mass divided by density, ms by rho s. ms by rho s. So, this is what is this, surface area per unit volume of the particles. So, the corresponding equation is 6 ms divided by rho s dP, where ms is normally taken as directly. If you want to use that equation, ms is weight per unit volume of the bubble free slurry. Very simple, no, to get that. Volume of liquid. This one is volume of liquid, right? We are not substituting, that comes by definition. So, in between only we substitute volume of particles and volume of particles and volume of particles. This can get cancelled. Okay? So, that means if I know what is the total amount of solids I am taking, total mass, if I know the density, if I know diameter of the particle, I can calculate AC. Kavya has doubt.
It's not dimensionally matched.
Tell me which one is different there. This is ms is the weight of the single particle, rho s is the weight of single density of single particle. So, that will be the volume of particle, right? Volume of liquid by definition I am keeping as it is.
Per unit
volume. Where is per unit volume? AC differentiates itself per unit volume. I mean, that is what in the beginning itself we have written only per unit volume of liquid, right? This is simply here volume of particles and this is also volume, but I know surface area per unit volume of particle. I mean, is there any problem? Not able to get that.
I'm not understanding why didn't you write volume of liquid?
Where is volume of liquid? Because I am interested here. See, I introduced here volume of particles, right? Per unit volume. Per unit volume, because the definition here is surface area per unit volume of liquid. See, normally what we will do, what we have to do is that volume of the surface area per unit volume of particle we use. Normally surface area per unit volume of the particle only we are talking, but the definition given here is surface area per unit volume of liquid. But this I can also write surface area per unit volume of particle multiplied by volume of particle divided by same volume of the liquid. So, that way I can use this equation to calculate AC. Similarly, can you also find out interfacial area of the bubble per unit volume of bubble free slurry? Same thing, same technique, but there you cannot use the density. So, Ag is surface area per same thing again volume of liquid, which can be written as surface area what is MB? That we do not know. Here you get another beautiful term. See, this is surface area of bubble divided by volume of bubble, okay? If I am inserting in between, right. So, surface area n number of the bubbles divided by n number of bubbles also, that will be simply 6 by dB. Then this side I have to write n into volume of bubble, Kavya. This side I have to write n into volume of bubble, okay, bubbles. And what is that? I think volume of bubbles I will simply put as VB. Is what? So, that is why finding out gas hold up is also very important in slurry reactors. Okay? That VB is the hold up, where we have now here 6 by dB into VB, volume of bubbles, and volume of bubbles by this will be hold up. Okay? So, this is, that means if you know the volume, this volume of bubble by volume of the liquid will be hold up. Please write that volume of bubble by volume of liquid will be the hold up. This is another equation. Then we have to substitute now what is the volume of the, what is the hold up of the liquid. Good? Okay, good. So, now we assume that we know this AC and AG, because once I give you what is the hold up of this, also can be written in terms of 6 dP into 1 minus or epsilon, not 1 minus epsilon b in the normal term. Epsilon is the void edge. Okay? So, that is nothing but hold up of the liquid. Okay? So, now this is another this may be equation 17, this is equation 18. So, now again another simplifications. If I am finding out that I have large number of small particles, catalyst particles, so that means I can neglect now this term, because AC is very large. So, 1 by AC, because large number of very fine particles. So, that means this surface area is very large. The surface area is very large. I cannot neglect this, but I can only neglect this, right. Okay, good. So, if I do that, what is the rate expression I get? Go to ROB. If AC is very large, naturally AC by AG also will be large. So, in this equation we can neglect only this, then what is ROB? Huh? KL into, excellent, KL into AG into CL. That is what. So, now what I am trying to say is Ag contains what? Now, everything has focused now on Ag, but if I want to calculate Ag, what I should know? This is not dp, this is db, hold up and diameter of the bubble. So, I am just trying to pose the problems to you. Okay. So, now hold up in the that is the reason why in most of the time in heterogeneous systems we are worried about hold up. I have been telling this long time. In hydrodynamic studies we always try to find out what is the hold up, correct, no, many times I have told that. So, these are the problems now, you are now really facing that, right. So, when I want to use this equation, all my focus AC is there, but all my focus is only Ag, but Ag now depends on dB, and how accurately I measure dB is important thing for me. How do you measure bubbles in slurry? If I ask you in aquarium you have fish is moving, but gas bubbles also are moving. If I ask you to find out what is the diameter of that, how do you find out?
Bubble free volume, we subtract that with the volume.
Yeah, that is the most engineering way of doing things, but what is the assumption? All the bubbles are same, okay, bubble size, but clearly you know that the bubbles are not same. That is what someone told centipede has 100 legs, but anyone counted whether centipede has 100 legs? Okay. Similarly, here why I am telling is we believe many things. So, one of the simplest way of finding out bubble size is that you measure the volume without introducing the gas of the liquid, then introduce the gas, because gas has volume, so it will get volume will increase. So, subtract that increased volume minus this liquid volume, then assume that you have bubble size, uniform bubbles. Then how do you calculate bubble size now? Spherical bubbles.
So,
how many number? Whatever number you have, whatever number you can get some other value. See, diameter I have to, all that volume now, increase in volume, I will say that I have 1000 bubbles, and then each bubble has 1 millimeter. Huh?
Something like a Taylor bubble, so that it will only one.
What is the use of that?
So it will have only one bubble.
I don't have one bubble, I have thousands of bubbles inside.
So what we do the Taylor bubble experiment?
Taylor bubble experiment is to find out the characteristics of the bubble. Okay? But here in the presence of so many large bubbles, how do I find out the volume? I mean the size. So, normally what we do is, that is why we do most of the experiments in transparent perspex columns or glass columns. We will now approximately find out, maybe by looking, carefully observing, okay, this may be 5 mm. Okay, all may not be 5 mm. You see how many approximations are involved. Particularly Abhinav was asking yesterday some question, because engineering is approximation. Like that in bubbling bed model also there are many approximations. Okay, but now no, I am a scientific engineer, not engineering scientist. Okay. Now, I want to find out exactly the bubble size, that is where is the challenge for you now. First of all, you have to find out how many bubbles are there, and you find out how many bubbles are with 1 mm, 2 mm, 5 mm, 10 mm. So, that means you are talking about bubble size distribution, challenging task for chemical engineers. Even now we do not have a good method, it is approximate. That is why there are many challenging problems, I say, and people live with bubbles, drops, and even how do you find out drop sizes in liquid extraction? Thousands of people are working on liquid extractions in industry. They are producing wonderful products after extraction, but still we do not know how do you measure drop size. Same thing here, bubble size. Only we are sure about particle size. That is all. I think because particles are not changing in time, okay, size wise, unless you have tremendous attrition and all that. So, particles are the things only we can characterize, and there are many theories. I do not know, you are not in DD, no, none of you are in DD, all of you in BTech. Okay. So, they have a course called multi-phase systems. Okay. I think MTech you also have that course. Yeah, entire multi-phase system is only to talk about bubbles, drops, particles. That is what is entire multi-phase. Okay. So, every time what you say, all this finding out hold ups, because each system will have a different hold up, right. Bubble liquid, no, gas liquid columns different, and gas liquid solid different, fluidized bed different, packed bed different. So, like that you can list out, rotary kilns different. What is the normal hold up we use in rotary kiln? Because luckily they are solids, they are not changing. So, that is why you said that it must be less than 10%. Yeah. Okay. So, why can't you use 90%? Yeah, just yeah, Kavya, why can't you use 90%?
They will be contacting
Can't
mixing won't happen.
how
Mixing won't happen.
yeah, mixing will not happen, and there will be contacting, but I think the way you expect particle has to will be lifted to the top and then fall, again lifted to the top, again fall. So, like that kind of beautiful motion is not there. So, that is why 10% or less than 10% is fantastic. Same thing even with centrifuging, if you go to that level of RPM also only 3-4. If you go to 100 where centrifuging happening, then what happens? All the particles stick to the walls as if it is part of the wall. So, where is the contact? All the gas will go in the central annular region, and very small contact will be there. But whereas, when you have this normal method what you are operate with low RPM and low hold up, goes falls, there is now more residence time for the exposure and good exposure. Okay. So all chemical engineering equipment is really a thrill to design, even though there is no romance after derivations. Okay. Because correlations may be boring, but still that is what is life. That is what is life. After you marry, I think you remember my words. It is routine. It is routine. Every day get up, take breakfast, go to work, afterwards come, and if you are in very good mood, fight with the wife. If you are not in good mood, go to the room and then sleep. So, all these kinds of, that is routine till we die. Same thing here also, correlations. Even though we develop theory, every paper has a new theory, but how much of that is used in chemical engineering equipment design is very small. That is why you have to appreciate chemical engineering. Whereas, any theory, every theory developed by computer science engineers, electronic engineers is thrilling, immediately it is applied to the field. But mechanical engineering, chemical engineering is not that easy. Mechanical engineering is particularly, it is not that exciting because they do not have chemicals, they do not have so much equipment, they have only one equipment called IC engine. Okay. Only outside shape will change, okay. Bonnet may change, or that front design may change, tires may change, or top they may put that ladder or may not put ladder, that is all what they can do. Engine is always engine. I think 1800s they invented, it is same thing, not much improvement. Only thing now we are trying to do is that put better petrol, or put some oil, put some this one alcohol. So, and then trying to find out how the car goes. Okay. So, that is all. I mean, other than that, even aeronautical engineers, their entire life is only one engine, correct? No, jet. That is all. They may be trying on that variations, but for us, even one process there are thousands of variations. Just one process. Packed bed alone, how many ways you can design? Fluidized bed, how many ways you can design? Okay. So, you can try to put somewhere input, somewhere inlet, somewhere outlet, multi inlet, multi outlet, all the things you can try just to get good efficiency. Okay. So, that is why this is the equation, and now this AJ to find out we need correlation. That one correlation I will give you for dB, there are many. dB correlation, yeah. So, now I just want to trying to tell you the connections one after the other. So, dB now, because this AJ depends on dB, right. So, now we should have a dB correlation. So, 1.35 U by G delta by delta U square rho L divided by sigma L to the power of half into rho L delta G, no, sigma L, not rho L, rho L whole to the power of 1 by 3, where simplest thing of course is dB bubble diameter centimeters, okay, and we have U gas velocity, yeah, this is again particularly for this is only for porous plate. Please remember, porous plate is different than perforated plate. So, if you have perforated plate, you will have different correlation. Okay, yeah. So, U g is gas velocity through porous plate, centimeters per second. Then we have delta pore diameter of porous plate, then sigma L here is used as surface tension, that is ergs per centimeter surface tension, yeah. So, that is the one erg per centimeter, and then you have rho L of course density, of liquid grams per centimeter cubed, yeah. Anything else? All those things are covered. Huh? Oh, dynes per second, not centimeter. No, second or centimeter? Centimeter only. Length, dyne. Okay. So, like that it goes on and on. Good. Okay. Fine. So, I think the next part is Sridhar, sorry, I think it may take some more time, but you don't fall, no, because there is no breakfast. Okay. So, good. Now, we have sufficient information now for the rate expression. You know how to derive the general rate expression and how to get the constants that are involved, K L, K C and all that, K G and all that. So, then you also know how to find out that A G, A C, all that information we have now. Now, it is application to slurry reactor. So, application to slurry reactor, this is very simple, it is not that difficult. Good. So, we will have the slurry reactor design. Okay, I will write here design. We have the slurry reactor. Okay, I think maybe let me close this and then put. So, you have bubbles, yeah, we have particles and we have liquid, right. So, I am taking now that one thing is that we can also take based on liquid phase, because we want to design now, right. So, your interesting phase may be liquid. If it is liquid, that is equivalent to batch liquid, and you have the rate expression. What is the equation? T by C A naught equal to, it is liquid, integral 0 to x A dx A by minus R A. This minus R A is that. If it is plug flow for gas, so solids is in batch, but solid is a catalyst. So, we are not going to try anything on that. So, when it is gas, one assumption is that it is moving in the form of plug flow. So, then we will take a small, because again that approach only I am trying to tell you, this is delta z, this is z plus d z, this is z, that is delta z. Okay. So, in a simple manner, if I have cross sectional area A, when you have, or otherwise if I write in our normal plug flow fashion, ideal plug flow FA plus DFA. Okay. Now, I have to write the material balance. Moles entering will be FA, right? Moles entering will be FA, because you know that is why I am not writing that. That is input equal to output is FA plus DFA. Please remember, it is moles per second all the time. Savita, moles per second. Yesterday also we did the same, moles per second. Plus, it is a continuous reactor where there is no accumulation for the gas. Gas is moving continuously. So, then that accumulation equal to 0 plus reaction. What is reaction? Minus ROB. Okay, I have not written. Okay, the same thing into dV. This dV can be, this is dV, which can be A into dz, AC into dz. So, now tell me what is the equation you get here? Oh, time to stop. FA will get cancelled. So, minus FA equal to, can you tell me the integral expression? You can leave it as length, you do not have to write. In terms of V also we can leave it as it is. V by, this will give me V by integral expression I am asking, dxa by, that is the one. So, now this volume is not simple volume in meter cube, but that is volume of liquid, volume of bubble free liquid. Why? Because here what we have used is volume of bubble free liquid. This balance what you are writing, this must be only bubble free liquid. That is only thing you have to take care of in heterogeneous systems. What is that corresponding one what you are writing? Okay. So, because our ROB is defined as the volume, moles converted per unit volume of bubble free slurry per time, right. So, when I am multiplying to get moles per, if I write moles per time, I have to multiply only by that corresponding V. That is the only thing which you have to be careful when you are writing the material balance for heterogeneous systems. So, this is again nothing but your ideal plug flow equation. That is what I have been telling. Okay. Minus ROB. Good. Now, if it is a first order like this system, what we have? So, the CL correspondingly can be converted into 1 minus XA, CA naught into 1 minus XA. Then that you substitute and then we can integrate. That is all. That is why I told you, in fact, contacting is much easier to remember, right. Whereas, it is heterogeneous reaction rates which will give you hell. Already this is one hell, yesterday another hell, because fluid aged bed, and sometime before packed bed another small hell, because in packed bed things are not moving except gas. So, that is why, and we have not done again moving bed again will be another hell. But what you have to remember is the mass transfer coefficients and heat transfer coefficients will be changing the moment how the phases are moving change. The movement of phases will determine mass transfer coefficients and heat transfer coefficient. That is the reason why for each and every equipment you have different mass transfer coefficients, different heat transfer coefficients, whereas reaction rate is same for any system. Reaction rate that will not change. So, that is the reason why heterogeneous systems are very beautifully exciting things. And to close, we will go back to, we started with this. I told for anything which starts which has everything that starts with a beginning will also end. So, now we will end here with the same diagram. So, this is reactor input, output, kinetics, contacting, So, here I have a batch PF continuous, sorry, continuous, then we have PF, MF, here we have physical, chemical. So, performance equation is output okay, Shekhar, remember, is a function of kinetics, contacting. So, that is the one, and now of course, here what you are trying to say is that we are only talking about all the time ideal contacting. So, the moment you have non ideal contacting, this equation will change again. So, that will be more and more complications only, other than that there is nothing. Okay.